We're surrounded by a completely invisible world, the world of molecules. I mean, they're the building blocks of, well, everything, but they're just way too small to see. So, what if I told you there's a way to not just find them, but to build a super detailed map of them atom by atom? All right, so let's dive right in with the big question. How in the world do scientists actually see something as impossibly tiny as a molecule? I mean, you can't use a normal microscope, that's for sure. So, what's the trick? Well, the answer is as elegant as it is mind-blowing. They listen to them. Seriously, they tune in to these really specific frequencies that individual atoms are broadcasting from inside the molecule. Think of it like this. It's like trying to identify every single musician in a massive orchestra just by the sound of their instrument. Okay, so to get our heads around how we can basically eavesdrop on atoms using this technique called NMR, that's nuclear magnetic resonance, here's the game plan for this explainer. First, we'll talk about a compass inside the atom. Then, we'll figure out what makes a nucleus NMR active. After that, we'll get into the dance of resonance, find out why hydrogen is the absolute star of the show, and finally, see how we actually decode the signal we get from the atoms. All right, first up, a compass inside the atom. This is really where it all starts. It's this fundamental idea that some atomic nuclei behave just like tiny microscopic magnets.
So what's behind this? It's a property called nuclear spin. Now don't worry, we're not going to get lost in the weeds of quantum mechanics here. All you really need to picture is that certain nuclei are always spinning. And just like a spinning dynamo, that motion creates a tiny magnetic field. It basically turns the nucleus into a little compass needle, right there in the heart of the atom.
But what's really fascinating is that not all nuclei do this. On one side, you've got your magnetic nuclei, like the regular form of hydrogen. These are our little compasses, the ones our instruments can see. But then, on the other side, you have non-magnetic nuclei, like the most common type of carbon, carbon-12. No spin, no magnetic field, so for this technique, they're completely invisible. So that brings up a really important question, right? How do we know which atoms are magnetic and which ones aren't? Well, let's look at the pretty simple rules that tell us if an atom is NMR active. Believe it or not, it all just boils down to counting protons and neutrons. A nucleus is going to be magnetic if it has an odd mass number, like hydrogen 1 or carbon 13, or if it has an odd atomic number, like nitrogen 14. So here's the key takeaway. If a nucleus has both an even mass number and an even atomic number, think carbon 12 or oxygen 16, their spins just kind of cancel each other out, and poof, they're invisible to us. It's a really simple counting game, but it has huge consequences for what we can see. Okay, so we've established that we've got these tiny atomic compasses hanging out in our molecules, but so what? How do we actually get them to tell us anything? Well, this is where we get to the real heart of the technique, the dance of resonance. It's how scientists basically get those little compasses to sing. And this breaks the whole process down into 3 really simple steps. So, step 1 is align. Normally, all these tiny nuclear compasses are pointing in totally random directions. But when we put them into a massive, powerful magnetic field, bam, they all snap to attention and line up with it. Step 2, flip. We then hit the sample with a super specific pulse of radio waves. This pulse has just the right amount of energy to knock those nuclei out of alignment, to literally flip them over into a higher energy state. And finally, step 3, relax and detect. We switch off the radio pulse. Now the nuclei can't stay in that excited state for long, so they relax and snap right back into alignment with the big magnet. And as they do that, they release that little bit of energy they just soaked up. That energy release is the signal we can actually detect. So that whole dance has a name, of course. That's resonance. It's just the scientific way of saying that the nucleus is absorbing the perfect little packet of energy from that radio wave at exactly the right frequency, all while it's sitting in that big magnetic field. A great way to think about it is like pushing someone on a swing. You have to push at just the right moment, at its resonant frequency to make it go higher. Same idea here.
Now, here's the thing. We can do this with a few different kinds of atoms, but there's one that just completely steals the show. So let's talk about why hydrogen is a star, and why what's called proton NMR is by far the most common type you'll ever see.
This one number is a huge part of the answer, almost 100%. I mean, nearly every single hydrogen atom that exists is the NMR active kind, hydrogen 1. It's absolutely everywhere, and it's always ready to sing for us. Oh, and there's more. It's not just about how common it is. Hydrogen also gives us the strongest, most sensitive signal you can get from any common nucleus. And when you think about it, Hydrogen is a key ingredient in pretty much every organic molecule imaginable. I'm talking everything from the fuel in your car to the DNA in your cells. It gives us this incredible window into the structure of the world all around us. Okay, that brings us to the final and I think most amazing part of this whole story. How do we go from just detecting a little blip of energy to creating a detailed map of a molecule? Well, this is where we get into decoding the atomic signal. This right here, this is the real magic. See, the exact radio frequency needed to make a nucleus flip isn't the same for every single atom, even of the same element. Why? Because it all depends on its neighbors. The electrons and other atoms right next to it act like a tiny shield, and they slightly change the magnetic field that one specific nucleus feels. So a hydrogen atom stuck to an oxygen is going to sing at a totally different frequency than a hydrogen struck to a carbon. Every single one has its own unique voice based on its exact spot in the molecule. So by collecting all of these different signals, all these distinct musical notes, right, scientists can basically work backward. They can look at the data and say, okay, that signal there, that's got to be the hydrogen over here on this part of the molecule, and that one belongs to the hydrogens over there. Piece by piece, they assemble the entire molecular puzzle, and that's how they figure out its exact structure. And that kind of leaves us with a pretty fascinating thought to end on. We've gotten really, really good at listening to hydrogen. But remember, this technology works for any NMR active nucleus. So the question is, if we can listen to hydrogen, what other atoms could we hear? What kind of secrets could carbon or phosphorus or nitrogen tell us about the molecules that make up our medicines, our materials, our very bodies? The orchestra is huge, and we're really just beginning to learn how to listen to all the different instruments.